So I'm going to go through Chapter 2 relatively quick because you can watch other lectures online. So Chapter 2, basically, it just talks about energy, and it's the first law. And so we've already talked about the first law. It says that there's an equation of state. And that equation of state is of internal energy. And so I can put delta E for internal energy. It really says internal energy, but now I'm putting change in internal energy. So internal energy, change in. Okay, and then I can write it in equation form. And it also says that heat's a form of energy, and I put it in equation form. So I'll just use delta U minus W. And so this is work on the system. So work on the system and heat, and both of these forms of energy. So both are forms of energy. Couples heat with equation of state, state to the system, or change in the state of the system based off of heat in and work in. So there's other forms of energy. It's not just heat and work and internal energy. There's many forms of energy. There's thermal energy. And so I can relate that to Boltzmann constant times the temperature. And just as a reference, kBT equals about 25 milli-electron volts at room temperature. So if I look at a computer and there's a thermal energy, and I look at the silicon chip, and I look at the energy associated which you need for a logic storing. So if there's thermal energy that's greater than the energy required to flip from a 1 and 0 in the logic states of a computer, that means thermal energy can erase memory. So this is important in future computers where we're getting faster and faster and smaller. But we have thermal energy. Thermal energy is important. Everything, you can just relate it real quick to kBT. And then there's also mechanical energy. And this, the mechanical part, we'll talk about throughout the course. Okay. We will talk about throughout the course. Kinetic energy, of course, we will talk about that also throughout the course. If I want to put another, I could put some EKIN. And then if I want to relate that and put it in equation form, I could say it's 1/2 mv squared. And so if I draw some particle, right, or I should put, I have some mass traveling at a velocity. Given that I have a mass traveling at a velocity, I can give it a kinetic energy. Well, coupled with mechanical, so mechanical has a kinetic part and also has a potential part and also has an inertial part, but, or I should say, it has a kinetic part. Here I just drew 1/2 mv squared. There's also a rotational kinetic energy, so I omega squared. I'm not going to put that here. But then also related to that, I have a potential energy, and so I could do the same, E potential. And then if I want to write it in simplified equation form, mgz. And so if I have my mass, and then there's some distance, sea level, okay? So I have some distance between some reference point and here in a conservative force, gravity, I can give it a potential energy. And so we done, you know, this mechanical, kinetic, and potential is all related to what you've done in freshman physics. Then we also can, you know, the other form of energy is electric, so I can be electric. And so if I have a plus and minus charge, a dipole, and so I can give it here a dipole moment. In electric field, there's going to be energy associated with that dipole. I could also write IV delta T. So IV gives me the power for electric current running through a circuit. And so if I just multiply that by some time that the current flows, I get an energy associated electric energy. I can do magnetic energy. And so here I have a magnetic moment. So this is a magnetic material. So I could say like north and south pole in some magnet. And then I have that up in an external magnetic field. And then it ends up being the dot product between these two. So when I apply this, if I have my magnetic moment 90 degrees with this, I have a maximum magnetic energy associated with this magnetic material. And then there's chemical energy, pretty straightforward. I just have some energy associated with the reaction, so I can do water splitting. I can take two H2Os and I can make two hydrogen molecules and an oxygen molecule, or I can take gases and go back. And then nuclear energy, and I can have fission and fusion reactions and whatnot. So there's many forms of energy, and we're interested in this. And so the internal energy of the system, or the change in internal energy of the system, that's going to consist of a thermal, right, electric, magnetic, chemical, nuclear. That's all the forms of energy within my boundary. So this right here tells me the change in energy within a boundary, and that's all forms of energy. You can consider it thermal, you can consider it potential, you can consider it chemical, you can whatever it might be. We don't need to look at all of this stuff, we just need to dictate. We have to understand that it's all the forms of energy within a boundary. So, related to that, all the forms of energy in a boundary, internal energy. And so let's draw a boundary. Okay, so I have my boundary, I have my system, I have my surroundings. Given I have my system, there's a temperature, pressure, volume, mass of my system. And from that, I can define the internal energy and entropy of my system. So I have a system, all the forms of energy within my boundary is defined as my system, gives me the system and its internal energy. I have my surroundings, everything outside, and the simplest way is just to define the temperature and pressure of my surroundings. So I've already wrote this, so I can write a change in internal energy, or delta U minus work on. And if I have an adiabatic boundary condition, that means that no heat is allowed to transfer between my surroundings and my system. So I could say Q is equal to 0. So this means that this represents the heat in. And so there's no heat in. And of course, in this format, I'm already implying that there's no heat out. So if I have it like that, and so this is adiabatic. And so the change in internal energy is equal to the work on. Another way to write this is I can say the internal energy at state 2 minus the internal energy at state 1 is going to equal the work on the system. Now I just want to point out in this form where I say adiabatic, I'm saying this, okay, Q is equal to 0. But Q is equal to 0 can also imply that Q in equals Q out, which implies that Q net is equal to 0. When I wrote it in this form, I just said that Q out was 0. The way I've asked you to memorize the first law. I wrote that this Q out is 0 and it's only heat in. But in general, I can write it more explicit, in a broader context, and I could say Q in minus Q out is equal to the change in internal energy minus the work on the system. And if I have adiabatic conditions, that means that Q in has to be balanced by Q out. So adiabatic conditions, you can have heat transfer, but it has to be an equal balance. The total amount of heat in has to be exactly balanced by the total amount of heat out. So the net heat transfer across the boundary from my system to my surroundings, or to my system, from my system to my surroundings, or from my surroundings to my system has to be 0. Okay, so I feel like I've talked about internal energy a bunch, but the main thing I'll say again, is you define a boundary which separates your system from your surroundings. Internal energy is all the forms of energy within that boundary. So if I have a magnetic material, that means it's magnetic energy, chemical energy, thermal energy, and whatnot. All the forms of energy. If I just have a gas that's non-magnetic, that doesn't conduct electricity, then it's just thermal energy. Okay, so sensible energy. This is the internal energy of a system. So again, I go back to internal energy, sensible energy, internal energy of a system associated with degrees of freedom of kinetic motion. So what are the degrees of freedom of kinetic motion? Rotation, vibration, spin, translation, so just as a context, S equals KB, natural log of omega, number of states, or degrees of freedom. So number of states of the system, omega. And so sensible energy, so we can say that the internal energy is coupled to the entropy, or the internal energy, the sensible part of the internal energy is coupled to the entropy. Okay, so I have sensible energy. I can also have sensible heat. Bless you. So sensible heat, so I use sensible energy, heat. So this has energy. So now it's heat, exchange, transferred or flow by a thermodynamic system where the sole effect is a change in temperature. So heat, sole effect, change in temperature. Sensible heat. So I can write an equation for Q sense is equal to the mass times the heat capacity times delta T. Or I can make a big C, P, delta T. So this is the heat capacity. This is the specific heat. This is the heat capacity. But anyways, I have sensible heat. Sole effect is the change in temperature. I take ice at 0 degrees C, or let's say minus 10 degrees C, and I add some heat, and then that brings me ice at 0 degrees C. There was amount of heat that was added. I can say this is state 1 and state 2. I add heat, and the sole effect was just to increase the temperature, taking ice from from minus 10 degrees C to 0 degrees C. Given that the sole effect from here to here was a change in temperature of my system, I can say that this heat is all sensible heat.
And if you melted the ice, the heat that melted the ice would not be sensible.
So the energy associated with taking the ice to water is not sensible. Yes. So coupled with that, so I had sensible energy above, and now I have latent energy. So the question was related to phase change. So latent energy is the internal energy, again, internal energy of the system. So everything within the boundary. You can see that sensible heat had said nothing about internal. This had to do with transfer of heat from it changed the internal energy of my system. Sensible heat. This is internal. So internal energy due to phase change. Latent energy. Latent heat. So here, unlike sensible energy and sensible heat, I can exchange energy and heat. I cannot exchange the term energy and heat. They have different meanings. Latent energy, I can exchange energy and heat. So energy Heat is a form of energy. And in this case, they end up being equal. Here they're coupled. Here they're equivalent. So the internal energy due to phase change. So the reason why I can do this is, well, it's usually done that way. But so when I have a phase change, there is, from a thermodynamics perspective, there is no change in temperature of the system. So if I look at the temperature between two states, so I can say minus 10, so I can put T1 is equal to minus 10 degrees C, and T2 is equal to 0 degrees C. So there's no change in temperature from here to here, but if I add some more heat, and I'll call this latent, LAT, and now I have water at 0 degrees C, and so I can say this is state 3, and I have T3 equals 0 degrees C. Here I have all solid water molecules, here I have liquid molecules, and so this part, delta T equals 0. For example, T3 minus T2 is equal to 0. So here I take a cube of ice at minus 10 degrees C. I heat it up to the temperature for phase change. Then I add more heat and I go through a phase change. So there was to go from state 1 to state 3, I had to add heat, both sensible and latent heat contributions. So latent heat, there's two. I can go from liquid to ice and ice back to liquid, right? And so that's the latent heat of vaporization. And then I can have latent heat of fusion. Well, actually, this was fusion, sorry. So ice to water, water to ice is latent heat of fusion. And then I can go from water, I could add additional arrows on this, and I could bring my water to vapor. I could boil it. So then I would take my water, I would heat it up to 100 degrees C. I would have a sensible heat contribution of taking 0 degree water and heating it up to 100 degree water. And then if I convert all that water to water vapor, I would have a latent heat contribution associated with bringing it from water to this. And so that would be the vaporization, and this part would be the fusion. So just as some numbers, liquid water to water vapor, the latent heat of vaporization is on the order of 2200 kilojoules per kilogram, and the latent heat of fusion is on the order of 300 kilojoules per kilogram. So we can see that this latent heat of vaporization is much greater than latent heat of fusion. This is general for most materials. And in fact, I think it's general for most materials. And so if I want to do this, I can write in equation form, Q is equal to M, latent heat of vaporization. So I have my mass, so I have this, and so I can break this into components. If I go from, I could add some M, Cp, delta T. So this is my latent, and this is my sense. So Soul effect, changing temperature. Soul effect, phase change. So if I add heat and I heat up a liquid and change its phase, I'm going to have two contributions. I can break that down to latent and sensible contributions. So latent energy, latent heat. Just said this, no change in temperature of the system. Delta T is equal to 0. Sensible energy, sensible heat. I can't exchange Soul effect, change in temperature. Of the system, delta T does not equal 0. T2 minus T1 equals delta T, which does not equal 0. Okay. So more on heat. We've been talking about heat. And we've introduced heat as a form of energy. But we haven't really said anything beyond. So if I were to ask you to define what heat is, other than saying it's a form of energy coupled in the first law of thermodynamics, and I want you to write in a sentence to define what is heat, it's like, what is heat? It's like the first time you learn about torque. It's easy to say R cross F, but to really define, other than saying R cross F, when you learn about torque in freshman physics, it takes some time, and you probably need to work with engines before you can give another type of description. It's kind of the same way with heat. I'm going to give you some wording on how you can define heat. And so energy transferred, exchanged, energy flow, or energy absorbed between two systems So energy transferred, exchanged, flow, or absorbed. Two systems, so it has to be across some boundary. Now, I can get internal heat generation, but between two systems. So when I have internal heat generation, that kind of gets a little bit complicated because then it's hard to define a boundary. But that's, the two systems are the system at two different states. Before internal heat was generated, after internal heat was generated. So two systems, that kind of gets to two states. But in general, let's just think of two systems. For example, surroundings, okay, and system. And I can have heat transfer. So I have my surroundings and system, and I have my boundary. So energy transferred, exchange, flow, or absorbed between two systems, i.e. system and surroundings. By, this is the key part, purely thermal interactions. So what is a thermal interaction? Purely thermal interaction.
Radiation.
Yeah, it's coupled with that. So let's think of radiation from the standpoint of how do you define radiation? Let's just consider radiation from the sun and radiation from let's think of heat radiation. From the sun and from the earth. The earth also radiates heat. Okay, wavelength. Thank you. So immediately he was thinking wavelength and the temperature corresponding to a wavelength. Wavelength. So how does wavelength couple with pure thermal interactions? Think of the states of a system.
Probably changes the rate at which the molecules move.
Move and vibrate.
Yeah.
So the exchange of vibrational, rotational, and translational modes, though that type of exchange can be considered a purely thermal interaction. So purely thermal interaction deals with these sensible energy contributions. Rotation, vibration, and whatnot. So if I have a molecule that's vibrating, I'll do it on here. right, at omega 1, and then I have something that isn't really vibrating at omega 2. And I'll try to draw the arrows to represent. And then I allow them to talk to each other. So there's a communication. At some point, if I relate this vibration to a temperature, and then I allow it to communicate with this molecule, this one's going to start vibrating more, and this one's going to start vibrating less. And at some point, if there's no extra heat that goes to the surroundings, they're both going to be at the same kind of vibrational mode, and they're both going to have a relatively same temperature. So you could see here this type of interaction of exchange of vibrational modes, it is coupled with heat transfer due to a purely, and we would consider that a purely thermal interaction. So as a material radiates, it's decreasing the vibrational modes in that material, and then it's shooting off electromagnetic waves, which then can interact with another material and increase the vibration in the other material. Another way to look at heat, just as a kind of a side note, Q, there's a small q, so I can write small q is big Q over m. So this is joules per kilogram heat per mass, or joules per kilogram. Sometimes we use small q, sometimes we use q dots, so heat flux. Okay. So heat by purely thermal interactions, this example I gave here, and so it's always convenient that heat is almost always quantified by change in temperature of the system. Now there could be a case where I have exchange in heat, but the temperature didn't change. So I could have more modes of vibration here. And so I could have purely thermal interactions, heat transfer, but that heat transfer didn't end up changing the temperature of the system. And then a phase change is an example. I change the state. So now when I have these vibrating like such, now when I have heat transfer, this is no longer distinguishable as it was. Now it's, we could put colors to this. And so after some interaction, I went from liquid water to vapor water. I went from liquid water to solid ice. So there was still some thermal interaction. I changed the vibrational modes. So the vibrational modes look different, but I also changed kind of the color. So there was still this purely thermal interaction. There's a new vibrational mode set, but it's completely different. So when it was ice, and so if it was water, I should probably did it a little bit different. You could talk with more neighbors. There was a cage structure of the water molecule. And then when it goes to ice, it's a different structure, a number of neighbors. So the vibrational modes are a little bit different. So in general, heat is most always quantified by change in temperature, but we do have phase change. And there is thermal interactions or heat for a phase change, but this still plays a role in terms of describing thermal interactions.
Could you also have a heat transfer where you had neither a phase change nor a change in temperature?
I guess in principle you could.
I imagine it would probably result in like a change in pressure or volume.
Yeah. So I guess you could. You could have heat transfer, and well, I guess okay. So in terms of you would need some type of change though. There'd have to be some type of change. It might not go from liquid to vapor, but you might have something that goes from being an insulator to a conductor. So there's such materials where they're insulating materials, they don't conduct electrical energy, and then they go through a more of a solid phase transformation to a different structure, and then they become electrical conductors.
That would still be a phase transformation.
Yeah, it's phase. So
Between two different solids.
I think as soon as you would say that the temperature didn't change and the vibrational modes went from one distribution to another distribution, you would have to say that that's coupled to a phase change. and that phase would be dictated by the omega for one distribution. So this one would have one given omega, and this would have another omega. And so the distributions would be different. But both of these omegas might show the same temperature. So there'd have to be some type of phase transformation or color. Okay, so always quantified. So if I consider adiabatic process, so this also means Qn minus Q out is equal to 0. And I'm going to look at this so I can look at some heat transfer between my system and surroundings. And so I can relate that as Q is equal to the integral from T1 to T2 delta Q over T dt. So in here I can also do or Q dot, the rate of heat transfer. And Q dot is equal to dQ over dt. And so if I just replace my d's with deltas, I have that here, or I can write it, so I can write this as the integral from T1 to T2 Q dot dt. And I know if I have an adiabatic process, then of course I can write this if I want to break it into components. I can integral from T1 to T2 Q dot in minus Q dot out dt. And of course I can bring the integral, I can break it. I'm just trying to emphasize the point that I can go from the total amount of heat transfer and I can couple that to a heat transfer rate. And when I do that, I always want to think of it in a calculus integral form. Yes?
Is infrared the only wavelength that people travel at?
Heat travels at all wavelengths.
Okay.
Infrared is one wavelength of the electromagnetic spectrum where heat transfers. But it goes beyond terahertz.
Even in the regular like rainbow colors, invisible light.
Yeah, but I mean in general, there's far infrared and there's a bunch of other wavelengths.
Think about your microwave.
Yeah, so the microwave happens at megahertz frequency or gigahertz frequencies. So it's 4 gigahertz your microwave works at. And a water molecule coupled with that, a water molecule, the time, if I draw a water molecule, so just give it on this. If I draw a water molecule that looks like this, so wait, I'm doing it all wrong. H2O, so I had it right. HO, okay, so draw it like that. So if I think of a time it takes for this water molecule, so I can say that it has some moment associated with it. The time it takes for it to rotate is on the order of picoseconds. Oh, not actually. Yeah, it's on the order of picoseconds. And so there's this time scale. Your microwave oven works at gigahertz. So it works at a frequency that where if I take 1 over that frequency, it corresponds. So it works perfectly to get this water molecule to flip around at that frequency. So this had a vibrational mode, a mode at which it could rotate, a speed at which it could rotate. So I could convert this picoseconds to a frequency, and that frequency would be on the order of 2.5 gigahertz. And so if I send an electromagnetic radiation at that corresponding frequency, then I get this thing rotating more and more, and so I increase the amplitude of that rotation, the corresponding, and so then I would have heating up. Okay, so let's get back to this. So I have this expression. And so this is the rate of heat transfer. And then this is an example of thermal interactions. So I could think of velocities, and then corresponding with this, I have some average velocity. And I also could have, if I have diatomic molecules, so I would have vibration like such, I could put a water molecule in here where I get some rotation, but I'm going to have velocities, and this one I can't say vibration because it's just a single atom. In here I can do that, so then I have some omega average and average velocity of my gas. So as my average velocity of my gas, translational velocity, and average vibration approach zero, that means that my temperature approaches zero. So this is just a pictorial. So if I had this and I had this, I could have some heat transfer between. So if my gas here wasn't moving, it had a zero average velocity, and then I took some other gas and I coupled it to here where it had a lot of vibrations and a lot of average velocity. I coupled the two. Then I'm going to increase the average velocity here, which means that my temperature goes up. And just a simple way of doing that is, sorry, yes, kBT 1/2 mv squared plus 1/2 I omega squared. So I have my thermal energy, which is coupled with the temperature, and then I have my kinetic and my vibrational part. So this is just a way to couple the two. And when I have two systems that get coupled, the heat, the change in purely thermal interactions is what dictates the change in temperature. So now just some side questions. So this kind of gets a little bit off topic, but not really. So think back to the first law, and then we're talking about heat. To take a system to lower temperature, heat must be removed. And then I'm going to just put the question. Always. So if I'm going to take a system and I'm going to reduce its temperature, is it a requirement that I remove heat? Okay. So you probably should be able to answer this where you know for sure before the quiz. Can you take a system to lower temperature without removing heat? That's another question. So, can I take a system and decrease its temperature while not removing heat? And then the third question that's coupled to it, can I take a system to lower temperature with adding heat? So I would suggest you think about it.